Pop quiz. In the acidic cleavage of ethers, which bond actually snaps? Is it the carbon-carbon bond, the carbon-oxygen bond, or the oxygen-hydrogen bond? Time's up. The correct bond is the carbon-oxygen bond. But here's the catch. The carbon-oxygen bond doesn't always break in the same place. The outcome depends on the kind of carbon attached to the oxygen, and that's the rule we'll uncover step by step. In this video, you'll learn what acidic ether cleavage is, how the mechanism works, when SN2 versus SN1 pathways occur, and how to predict which carbon-oxygen bond breaks. Let's start with the big idea. Strong acids, such as hydroiodic acid or hydrobromic acid, protonate the ether oxygen, creating an oxonium ion. Protonation turns the ether into a good leaving group. That makes the adjacent carbons vulnerable to attack by halide ions. So here's the sequence. Step 1, protonate the oxygen. Step 2, the halide nucleophile attacks. Step 3, the carbon-oxygen bond cleaves. On a primary carbon, the attack follows classic backside SN2, but there are exceptions. We'll see what happens with sp2 carbons next. Take anisole with hydrobromic acid as an example. After protonation, bromide cannot attack the phenyl carbon because it's sp2 and blocked from SN2. Instead, it attacks the methyl carbon. The products are phenol and methyl bromide. Remember, SN2 never happens at sp2 carbons. So far, we have 3 rules. Protonate the oxygen, attack the less hindered sp3 carbon, and never expect SN2 on an sp2 carbon. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Now, let's apply this to isopropyl ethyl ether with hydroiodic acid. After protonation, iodide attacks the less hindered ethyl carbon. The products are iodoethane and isopropanol. To make a mental shortcut, primary carbons usually undergo SN2 cleavage. Tertiary carbons can form stable carbocations, so SN1 takes over. Secondary carbons, they can go either way depending on sterics and conditions. For example, tert-butyl methyl ether in hydroiodic acid. After protonation, the tert-butyl side easily forms a carbocation. Iodide captures it, giving tert-butyl iodide and methanol. That's an SN1 cleavage. At higher temperatures, elimination, E1, can compete with SN1 when carbocations are involved. So the product mix depends on the substrate and on the reaction conditions. But not all acids are equal. Hydroiodic acid is the most effective. Hydrobromic acid works well, but hydrochloric acid is much less efficient. Why? Because iodide and bromide are strong nucleophiles in these conditions, while sulfate from sulfuric acid isn't. So here's the recap. A strong acid protonates the ether oxygen. The halide attacks the right carbon, and the bond breaks. Primary carbons go SN2, tertiary carbons go SN1, and at higher temperatures, E1 can sneak in. For a clean cut, choose hydroiodic acid or hydrobromic acid. That's the whole playbook for ether cleavage.
Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.